This presentation is titled Graph Neat Examples in Raku. My name is Anton Antonov. Today is November 13th, 2024. In this first example, we see undirected graph. This is a triangular grid graph, and I have colored the vertices according to their degree. This means the number of edges that go into each vertex. And here the corresponding adjacency and incidence matrices. The adjacency matrix is vertex to vertex, it's symmetric. This is an undirected graph, and the incidence matrix shows the vertex to edge relationship. So each column corresponds to an edge, and we can see each column has exactly two elements, non-zero elements. All right, so what are neat examples? They're concise or straightforward code that produce compelling visual or textual outputs. They showcase Raku programming. They also showcase functionalities of different Raku modules, and they give interesting perspectives on what is computationally possible. I'm using the package graph for this, as presentation says, and I'm visualizing the graphs using JavaScript D3, which is based on D3GS. It's a JavaScript library, D3GS. Also, graph package or the graph class has its own method called dot, which uses the dot language of GraphViz, and GraphViz can be installed on almost any system. Hence, we can produce the SVG images and visualize using dot. All right, so my second example here, it's like, actually, let me first show this graph. I don't want to do that. So I'm going to just make the vertex. Let's actually use the vertices, right, and visualize this in this way. So grid graphs, they're bipartite. This means that we have two sets of nodes or vertices, and each set, for each set, is true that the vertices in that set do not connect to each other, but they connect to the other set. So this is what we see here. We can see with this coloring, you can immediately see that grid graphs are bipartite. So let's actually go through this code. So here I'm generating a grid graph. I can verify that this grid graph is bipartite. You know, this method of the graph class. And I can also derive the corresponding bipartite coloring. I can use this bipartite coloring to derive the highlight lists. So you can see I'm using classify. This is the built-in Raku function. And then I'm making the actual code here. You can see, with the highlight and the vertex coordinates. So yeah, some of these grid graphs or other, known or named graphs in the graph package, they know vertex coordinates. So this is being leveraged here. All right, so next example, this is a little bit more complicated. It's again with a grid graph. I'm making it undirected, but I have, from this undirected graph, I am making it directed in a random manner. And so this is a much more complicated problem to find the connected components in a directed graph. In a directed graph, that's easier. And so let's actually examine what we see here. So the connected components are colored in the colored in different colors. So for example, this one here with I think very bright yellow. So you can see that each of these vertices can be, from each of these vertex we can reach any of the others. Now, why is this not in this set, right? Well, it can be reached from this 4 yellow vertices, but from this vertex we cannot reach any of those. So that's why it's not in this group. It's not in this connected component. Okay, so this can be visualized also with dot, but I'm going to use a different graph. Again, I'm going to use a triangular grid graph, and so here. Actually, let me demonstrate this here. So if I use the JavaScript visualization, this JavaScript library, we can see that JavaScript code is being generated, and it is being rendered in this Jupyter notebook, or also Raku chatbook. Jupyter framework uses, it's a web-based technology, so it is almost straightforward to render JavaScript code. Similarly, if we generate SVG code, which is what dot does, this dot method does, so we can again visualize it in Jupyter notebooks. So, and you can see here I'm using this dot language, but I'm also randomly picking the shape of the node. And so let me contract this here. And so sometimes it's going to be, okay, yeah. Sometimes it's hexagonal shape, sometimes it's triangular. There's a minor note here. I'm using both vertex and node in this method dot, because node is the terminology used in GraphViz or the dot language. I personally prefer vertex, but you can use both vertex shape and node shape, for example. All right, so moving on, the last example is a collage of star graphs. And I'm going to just plot it, and so show here. So let me untangle some of this, so this is probably the neatest example from this set, I would say. You can see that I have created 40 star graphs. Each of them has between 8 and 16 rays. And I have picked some subset of them and colored them. So I think this code was generated using large language models, but I didn't see. It would have taken too long to demonstrate that the actual generation. So yeah, so we can see, here we visualize this set of star graphs, and we can have fun manipulating them. All right, how this happens with dot? So the reason I'm showing the dot example here, let me zoom out. I mean, you can see, for example, how it is a little bit more regular than the one with JavaScript. The other thing is that instead of specifying the elements of the plot, all these colors and highlights and so forth, instead of specifying them as individual arguments in the dot method, I can actually use the dot language. The dot language, the DSL, which is dot for specifying graphs, it's not that difficult to learn, and it's it's very powerful and pretty straightforward, as you can see here, to make a preamble which specifies the style, and then use that preamble to make the plots. All right, this was it. Thank you.